Hello everybody and welcome back to another video. Today we'll be continuing from the previous video where we were going through the principles of atomic theory and the theory of mass spectrometry. In this video, we will delve further into the topic of atomic structure, where we will be discussing about the electron configuration and ionization energies in gaseous ions. In the previous video, we were discussing about the atomic model which everybody pretty much knows about, which is Bohr's atomic model, where electrons are assigned in different orbitals with different energy levels orbiting the nucleus as minute particles, which is correct to an extent in an A-level standard. In A-level we characterize electrons as clouds of negative charge which surround the nucleus and can take several shapes with varying energy level as shown on the right. These orbitals can contain electrons in different subshells, which can be an SPD or F subshell, where each orbital can hold a maximum of 2 electrons. An S subshell has 1 orbital, a P subshell has 3 orbitals, a D subshell has 5 orbitals, and an F subshell has 7 orbitals. So as a result we can deduce that an S subshell can hold 2 electrons, and a P subshell can hold 6 electrons, and so on, as each orbital can hold up to 2 electrons in each subshell. If you still do not understand the theory behind this, then it is in highest importance that you go over this slide again, as the understanding of electron configuration would be vital in order to understand spin diagrams, which we will cover shortly. If we look at the example in sodium, we can see that the electron configuration is 1s2, 2s2, 2p6 and 3s1. This is because we fill electrons from the lowest energy level first, which starts from s. When we talk about electrons in an atom, electrons are not static but move in clockwise or anti-clockwise motion across their respective orbital, which chemists represent this using arrows going up or down, or also known as spins in spin diagrams. The rules for displaying spin diagrams are filling the 1s and 2s orbitals fully with one arrow going up and down first, and then for all the other energy levels, filling one of each orbital with one arrow going up or down, then filling the orbitals after with the remaining electrons you have left. A clear example of this is shown with neon on the right, abiding these rules. Now that we have gone through the topic of electron configuration, we can now begin with providing evidence of the existence of electron subshells using data gathered from ionization energies. If we look at the elements of group 2 going down the group, as you can see, the ionization energy significantly decreases from beryllium to calcium and steadily decreases from calcium to barium. This overall trend is because of the increasing number of electrons, and hence there is an increase in energy levels, so there is greater shielding effect between the electrostatic force of attraction between the outermost electron and the nucleus, and because of this, it is much easier to remove the electron, as it requires less energy to remove it. This provides the evidence for the existence of electron shells. Interestingly, if we look at the trend in first ionization energy across a period, the overall trend is steadily increasing with some occasional dips. The general increase in ionization energy is due to the increasing number of protons in the nucleus. This provides a greater electrostatic force of attraction between the nucleus and the outermost electron, which effectively this pushes the electrons towards the nucleus. This as a result reduces the atomic radius and increases electrostatic attraction, so it becomes harder to remove the electron, which therefore increases the energy required to remove the electron. The occasional dips are present because these electrons are removed from lower energy levels than others. If we look at magnesium, the electron being removed is from the 3s orbital, and in aluminium the electron is being removed from the 3p orbital. The 3p orbital is at a lower energy level than the 3s, so it requires less energy to remove the electron, so there is therefore a dip in ionization energy. Try and also have a go at explaining why there is also a dip at sulfur using your knowledge. Thank you for watching this video. Please give it a like and subscribe for more future content, and don't forget to share the video with your friends. If you have any queries with this video, be sure to leave a comment and I'll get back to you as soon as possible, and as always I'll see you on the next one.